So it can feel as if there's uncertainty all around us. Every day we wake up to news feeds that are filled with information that is uncertain, unsettling, and sometimes downright terrifying. I should know I'm a cognitive scientist who studies uncertainty communication. And unfortunately, for the vast majority of the public, reasoning with uncertain information is very challenging, which is illustrated by the recent confusion associated with Hurricane Dorian's path. As many of you might remember, earlier this month, September in 2019, as Dorian was affecting the Bahamas, projected to go to Florida and the East Coast, President Donald Trump tweeted some confusing tweets about the path of the storm. Now, unfortunately, the misunderstandings that Trump came to about Hurricane Dorian's path are not unique to Trump. We all share these same types of miscommunications, and what I'm going to talk about today is some of the cognitive science around why we misunderstand hurricane forecasts and how we can all become more informed information consumers. So I'd like to start by saying that the way that information is presented has a profound influence on our decisions. For example, here are different color schemes you can use to color code your data. I'm sure almost everyone in here has tried to color code their data before. These are two different data sets that I'm going to show you. The first one is a two-dimensional data set. It should look like a sphere. It should be completely smooth and continuous. And this one here is a digital elevation map that is the underlying data used to create topographic maps. And this is actually an island off of Hawaii. Okay? And both of these are shown to you in grayscale, with black being the lower values and white being the higher values. We take these two underlying data sets and we apply a rainbow color map to them. They look like this. Okay? I'm going to toggle back and forth, and I want you to think about the differences as I'm toggling back and forth. Okay, what do you see? What are the differences between this visualization and this visualization? What are you noticing? Any thoughts?
More than two categories are very obvious.
Right, which ones are the most obvious to you?
The bright ones.
The bright ones.
Is that all?
Probably the green. So you're probably noticing this big area of green in here, right? And maybe some large swaths of blue. So one thing that's going on is that when you have the data visualized with these rainbow color maps, because the different color categories have the same representation, some information is being masked in here. For example, take a look at this real data feature right here. This is an area that's very steep off the island. In this version, it's completely gone. So this is a real feature in the data that people need to know about to make decisions with their visualization. And when we represent it with this rainbow version, it's completely masked. And one of the ways you can start to figure out if the visualization that you're looking at is manipulating the data is by taking a look at the legend. If we look in this legend, that portion of green is overrepresented. So that starts to give us a clue as to if this particular way of visualizing the data is not accurately portraying the data. Did you see any other differences between these two that you'd like to point out? Any other ones?
Sure. I mean, it's a lot easier to tell that it's a circle, like a very clear-cut circle.
Right. So actually, this isn't a perfect circle. It goes from 0 to 100 in a completely continuous way. But what you're pointing out is this looks like a circle that starts here. Yeah, right. So this cyan band here is an artificial feature in the data that's created entirely because of this rainbow color map. There's also, you kind of see in this projector, in this yellow section, there's also an artificial band that is not there in the data whatsoever. So in addition to masking features in the data, it's making these perceptual features that aren't there whatsoever. So it's entirely manipulating the way that we're understanding the underlying data. Let's look at one more. This is the default color scale used in Matlab. How many Matlab users? Okay, lots, right? So you see this particular color scale used in many neuroscience imaging papers because it's the default. We often use the default of programs. I'm going to toggle back and forth, and I want you to think about the differences between these two. What are you seeing? What are the big differences? One that I'll point out is that we're still seeing this effect where there's features in the data that are being created that are not there, but they're not the same. Look at this cyan band, and if we see here, it moves, just moving around arbitrarily. There's no rhyme or reason for why this cyan band should be here. It's not in the data at all, and it's just kind of moving around arbitrarily. So there's even differences between different rainbow color maps. There's no consistency here, and there's no rhyme or reason for why this is happening. It's just sort of an accidental feature of this particular visualization choice. And what we found in 2018 is that rainbow color maps perceptually discretize data. We see them as bands or sections rather than continuous information, which is a problem because they are continuous. The other issue with that is that the discretization happens in unpredictable ways across different data sets. So let's say you do want discretization for whatever reason. You want someone to see a yellow section and a red section and a blue section. That way that it is happening isn't going to be the same if you change anything in your data. So it's unpredictable across different data sets, and that's a massive problem. The whole point here is that the way that information is presented has a profound influence on our judgments. I showed you examples of color, which is a pretty basic choice in data visualization, but when you're visualizing your own data, you're making 3 to 10 different choices about how to actually visualize it, and all of those choices matter, and they interact with one another. So it's your responsibility as a scientist to make sure that you are clearly and effectively communicating your data with visualizations. So I'm going to tell you some of the cognitive science around how we can make better data visualizations. I'm going to start with this model here that we proposed in 2018. This model illustrates the visualization decision-making process, not learning or memory, but how we make decisions with visualizations. It starts here with a visual array, which is a very jargony term for visualization. Ends over here in a behavior or judgment. For the purposes of this talk, I'm going to call out just these two components here, which is working memory and a graph schema. Rather than giving you jargony definitions of these two items, I'm going to illustrate what I mean by the relationship between these two concepts. Okay, we have a figure here. It's a simple figure. It is showing you the population growth of species X over time. And it denotes when a predator species was introduced into the ecosystem. Now, if you're making a fast, snap decision, you might think, oh, well, when that predator species was introduced into the ecosystem, that correlated with a drop in the population of species X. Raise your hand. How many people see why that interpretation is incorrect? Very good. We have quite a few in the room. I'm going to give you a couple more seconds for those of you who are not familiar with this type of visualization to try to get it. For anyone who raised their hands, what did you see? Why is that interpretation correct? What do you think?
The y-axis goes from 1,000 to 0 instead of 0 to 1,000.
Exactly. So what he's noting is that the y-axis is incorrectly ordered. Now, in order to interpret this correctly, what you have to do in your mind is to mentally transform the data. And I want you to try to do that now. Imagine as if the y-axis is correctly ordered with lower numbers at the bottom, higher numbers at the top, and flip all the data in your mind. Give it a shot if you can right now. Okay, if you can do it, it looks like this. And then you would notice when the predator species was introduced, that correlated with the rise in the population of species X. And you might be thinking, this is a ridiculous visualization. No one would ever visualize their data this way. Oh, yes, they do. Here is a figure that is illustrating gun deaths in Florida, and when in 2005, Florida enacted the Stand Your Ground law. This was a real figure produced by a woman who works at Reuters that was released to the general public. Why did she visualize her data this way? What was she trying to make you think?
Stand your ground work.
Exactly. She's trying to make you come to the exact opposite conclusions about gun deaths in Florida. The way that information is visualized has a profound influence on your judgments, and people know that, and so should you. Okay? So what does this have to do with that model that I was telling you about? We have a visualization, and then we have a schema or conventions that we've learned to understand graphs. And maybe we had a great teacher who taught us these rules of thumb to understand visualizations, or maybe we've just picked it up through lots of exposure to graphs. And our schema suggests that lower numbers should be lower on the y-axis and higher numbers should be higher. And we just assume that's the case, unless we're very well-educated visualization consumers and we check to make sure that our assumptions are correct. So if we see a visualization and it doesn't match our mental representation, our schema for what it should be, then we have to do a mental transformation to make the two align. And as you saw, the mental transformation process is effortful. It requires working memory. It is not an automatic process. You have to deliberately decide to do these mental transformations. And okay, so working memory is a big topic in cognitive science that's very intricate, that's been studied for many, many years. I am using a vast oversimplification of it. For the purposes of this talk, I'll use working memory, sort of like cognitive effort, the amount of energy you're going to use to do a mental transformation. So that's how these two concepts relate. The idea of a schema, these rules that you have in your mind, and working memory, or the amount of effort that is required of you to interpret a visualization. So what do these tell us about hurricane forecasts? These are the types of images we're shown when hurricanes are approaching. And in 2017, we had 17 named storms and over 750 deaths. And that death count is from the US alone. Other countries have less of a capacity to count their dead, because death counts are very politically contentious topics. So their death counts tend to be much higher, but I'm not reporting them here. In a very developed country, we had 750 deaths alone, so you can imagine that the death count is much higher in other areas. Just this year, Hurricane Dorian, I think we had 54 deaths. And we are at the start of hurricane season. Due to climate change, we are going to experience a rise in the severity and the frequency of hurricanes and all natural disasters, and that's a fact. The things that I'm telling you about today are important because there's lots of people that this is affecting, but it's only going to affect more people in the future. So these are the types of images that were shown when these hurricanes are approaching. And I told you about color, right? The importance of color. Look at all these different choices that visualization designers are making. There's color and line and many, many different factors. So what we want to do in Matlab is to systematically evaluate the importance of some of these different visualization choices. Because the truth is, people are making these very complex decisions here, where they think about all sorts of things when they evacuate. Do they know their evacuation route? Do they have family members they have to evacuate with? Do they have enough money to evacuate? On and on and on. And this part of the decision should be as simple as possible. This part should be a no-brainer, so they can save all of the hard mental calculations they have to do for the really complex decisions. So that's what we want to do, make these easier. I'm going to show you a sampling from some of the papers that we've done in this space, and then highlight a specific study to talk about in detail. Okay, in our original work, we looked at different ways to visualize the path of a hurricane. There's different visualization techniques for that we've compared. We've also looked at animation techniques to represent the positional uncertainty and the intensity and uncertainty of a storm. Here we've looked at different tasks that people do with hurricane forecasts. This is probably my favorite paper from last year, where my collaborators came up with a new technique to make these paths. You might have heard in the news these lines, these hurricane path lines called spaghetti plots. They tend to be called that because they look, sometimes when they're poorly designed, look like a mess of spaghetti. My collaborators came up with this really cool new technique to reconstruct the paths so the lines are spread out nicely, and it sort of more fully represents the distribution. When you go from this to this, that gives you the ability to do some interesting things, like make the lines thicker, so we can put color on the lines to indicate the intensity of the storm, and now it's a cleaner visualization, so we can even put the size of the storm on there too. Really cool technique. I highly encourage you to take a look at it. And this process is not specific to hurricane forecasts. If you have any type of probabilistic estimate in which you're sampling from forecast data, you can do a similar type of reconstruction procedure to more accurately represent your distribution of information. In our most recent work in JP Applied, we've looked at how the number of different lines that you represent influence what people think about the visualization. For the purposes of this talk, let's start here. This is the current method used by the National Hurricane Center. It's called the cone of uncertainty, and it's been used since the late 70s. Can you think of another technology that we've used since the 70s? You know, bell-bottom pants are out, 8-track tapes are out, we're still using this cone of uncertainty. So it's based on a pseudo-normal distribution of information that they calculate from 5-year historical hurricane data, and they predict the mean path of the storm. That's what that center line is. And then they plot this confidence interval around that mean path, which is a 66% confidence envelope around the mean path. And it's intended to show you the general trajectory that the storm will take. Now, when we do experiments with these visualizations, what we like to do is to have people do behavioral measures rather than probabilistic judgments. People are very bad at reasoning with probability. Other researchers have demonstrated that in behavioral economics in very dramatic ways. So we try to avoid having them do a probabilistic judgment. For example, I've never asked you, what is the probability that this storm would hit Louisiana? If I were to be asking you that, I'd only be measuring your statistics training. Okay? Instead, we try to find a measure that people can intuit, that will give us some indication about how they're reasoning with this visualization, and includes uncertainty. What we've done in the last 5 papers is to have people rate damage associated with this storm. We have a scale with 1, no damage, ranging to 7, severe damage. And then we show them a location on the map, and we tell them this is an offshore oil platform. And give them just a little bit of information about what that means. And then we have them estimate the damage that would incur to the offshore oil platform. Then we move around the location of the platform to systematically test properties of this visualization. So we compare individuals' damage ratings, in this case, to modified versions. In this version, we made the edges of the cone blurry based on a Gaussian blur. And in another version, created by my collaborators, we're using what we call an ensemble display. An ensemble, like a group of things. And these are actually all based on the same underlying data. What you're seeing here is individual runs of our model, and these two are actually averaged over this space. So these are kind of like error bars. This is much like a scatter plot. All same underlying data, okay? But when we have people do damage ratings with these 2 cone versions, we find that people get higher damage ratings in these areas and less damage ratings out to the side. They see this as the danger zone and the safe zone, which is not how they're intended to be interpreted. When we have people do the damage ratings with this ensemble, they give higher damage ratings towards the central tendency of the storm and decreasing damage ratings off to the side. So this is indicative of them understanding the uncertainty in the storm's path. There's some way intuiting the uncertainty there, which is good. So we're finding a better technique than the cone of uncertainty, which is always good when you're iterating and developing. The other issue we find with these 2 cone versions is people think they represent the size of the storm growing over time. They don't represent any size information whatsoever. What they're intended to show is the uncertainty in the storm path growing over time. For example, I'm much more certain about a forecast for tomorrow than a forecast from 2 years from now. That's what you're seeing here, is we're more confident about where we think the path is here because it's close to when we made the prediction than in 72 hours from now. We're less certain. So why? Why are we seeing these errors with these 2 cone versions? And what we've proposed is that it has to do with that place in the model, the graph schema portion. We are showing people maps, and they're using their schema for maps. Completely reasonable thing to do, right? And the schema that we've developed for maps is that some place on the map there is a legend. And on the legend there is a scale. And in school you're taught you could even get your little ruler out and measure a point 2 locations on a map and be able to approximate the distance between those locations by making a calculation from the scale. And we've had that experience every time we've interacted with maps. It's very much ingrained in the way we interpret maps. If people were to interpret this correctly, they'd have to take the strategy that they've used their entire lives, suppress that, take this physical pixel width here, pretend it has no physical properties and remap it onto something abstract like uncertainty. And that remapping process is effortful, like we all saw in our mind when we had to remap. And that process produces significant amounts of errors if people even know to do it. Lots of people won't even try to do the remapping. They have no idea they should. And then if they do, it's very error prone. So that's one issue with these two types of visualizations. The other one that I don't always talk about, but I'm excited to bring up because we have some folks with linguistic expertise in the room, is metaphors. So Barbara Tversky proposed that when we deal with visual spatial information, there's a variety of metaphors that are elicited from that. And in this case, there could be a containment metaphor. What she proposed is that when we see boundaries around visual information, it elicits this metaphor of containment, where things inside of the boundary have a different status than things outside of the boundary, right? Reasonable. We see a picture frame. The point of the picture frame is that the picture is different than the wall. We put fences around our property to say, this is my property, not yours. So here we have a boundary. And so it's reasonable that it evokes this metaphor where whatever's in the boundary has a different status than what's outside of the boundary, which would be fine, except for this boundary is arbitrary. 66% was just selected. There's no scientific reason why we should care about 66%. It could be 65% or 67% or 95% might be a little bit more reasonable. This percentile was just chosen, and the implications of that percentile was not known in the late 70s, right? So that's kind of what we're thinking about in terms of the cognitive science. Oftentimes I get the question, do you actually see these types of misconceptions in the real world? Oh, here is a tweet from our commander-in-chief. He says, in addition to Florida, South Carolina, North Carolina, Georgia, and Alabama will most likely be hit much harder than anticipated. Shortly thereafter, the National Weather Service tweeted out, Alabama will not see any impacts from #Dorian. Well, why in the world did our president come to this misunderstanding and think that Alabama would be affected? Are there any reasons that he might believe that that was the case? Assuming he wasn't just kind of recklessly making things up, we'll give him the benefit of the doubt and say there's probably a reason that he came to this misunderstanding. So let's try to figure out what that is. Okay, here's the forecast from September 1st, the day that he made that tweet. This is the cone of uncertainty. This is Alabama. And notice the cone of uncertainty is nowhere near Alabama. And again, it is incorrect to think safe zone or danger zone, safe zone. That's still the wrong interpretation. But even if you were using that incorrect interpretation, the cone of uncertainty is nowhere near Alabama. But my close Twitter friend, Alberto Cairo, which I highly recommend following on Twitter, very progressive researcher, he pointed out that also on September 1st, this is what the wind speed probability map looked like. This is not the track of the storm. What it's actually showing you, probably can't read this, but it says areas within the outermost black contour have at least a 5% chance of receiving winds of 39 miles an hour or more. So what this is actually showing you is that that very corner of Alabama has a 5% chance of increased wind speeds. 5%. It is not going to be hit. There's a 5% chance of increased wind speeds. But in any case, Trump could be using one single schema to interpret these maps for all types of visualizations. He could be using the schema where he says, danger zone, safe zone. If he were to think that, then that would be one of the sources of the miscommunication. What are some of the evidence that he might actually be thinking that? Well, some of you might remember this. He annotated the storm track to circle that little bit of Alabama that was represented in the wind speed probability maps. So in some ways, he's kind of giving us an insight into what he was thinking the actual projection was, which looks fairly similar to the region affected by that wind speed probability map. What other evidence do we have? We have a tweet by him. He says, just as I said, Alabama was originally projected to be hit. He's using his evidence for hit as a probability wind speed map. He's showing us the probability wind speed map, the one that doesn't talk about hitting anything, just percentages of wind speed. And he's saying that's the evidence he has for making claims about Alabama. So this is some converging evidence that the president interprets virtually all hazard maps, regardless of what they're showing, as danger zone, safe zone. And the truth is, this isn't unique to him. We find these in our controlled laboratory studies as well. Okay, so what did we learn from this experiment? The main outcome is that this type of visualization doesn't seem to have these misconceptions. We're not seeing this inside-outside effect, danger zone, safe zone kind of thing. So we're done, right? We did a great job. We're wonderful scientists. Let's go on sabbatical. No. In order for me to feel comfortable endorsing this technique, I wanted to understand what types of schemas are elicited by this visualization. Because this is new. We can assume that people haven't learned how to interpret this yet. They haven't been taught. What happens when you see new information? You pull in heuristics or schemas from other contexts. Sometimes that can be good, but we don't know. So we need to figure out what schema people are using, and that will give us a very clear prediction whether this is appropriate for all people and what types of tasks this is appropriate for. So what I did was to survey the different visualization techniques out there, and I realized that our visualization shares a lot of properties with this type of visualization. This is a Google Maps screenshot showing your route from Merced up to Yosemite. And you're shown multiple routes to that location. I don't know if you remember the first time you ever used an application like this, but there was some learning that you had to do. You had to learn the conventions of what is being shown to you. It might feel intuitive now, but you did have to learn it at some point. And the things that you had to learn, the conventions, the schema that you've developed for these, suggests that you're shown multiple routes to a location. And these are deterministic, finite paths. You're not shown a distribution of paths. You must take one path, but not another, okay? And if people were to use the conventions that they've learned in this case to interpret this display, that would lead to some misunderstandings, and let me show you why. Here is an animation created by my collaborators, and it's showing the simulation plotted over time. Essentially, they take 5-year historical hurricane data and new initial conditions of the storm, and they make small perturbations to the model based on sampling from the perturbation space. And each one of these lines represents one of those perturbations to the model. That was a very jargony description of something that you could probably intuit by just looking at this visualization, which is that this outlier here isn't that meaningful. It seems to be just one outcome of many, many, many outcomes, and you should probably focus on where most of the lines are being grouped together. And you can kind of get that just by looking at the animation if I didn't tell you anything about it. But we don't show them this nice animated version. We show them the static version here. And in the static version, it is not intuitive that each of these lines aren't a predicted path of the storm, that these are just sampled from a distribution and they happen to be outliers. So the reason that we started with these static versions, this non-animated version, is because the majority of places that need the most help in terms of uncertainty communication don't have access to high-speed internet. They don't have iPads that people are walking around updating their information. Places like western coast of Haiti, which is where I worked, for example. So we wanted to start by making a static version as easy and effective to understand as possible, because lots of people only have access to this static information, if this at all. Okay, and then we wanted to move to the animated version. Lots of times you see talks where they propose that, the best new technique is this animated version of our application where users give us information and we update, blah, 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 blah. That's really great if you want to exclude a large portion of the population. So we tried to focus on something that would be accessible. But at the cost of animation, it isn't clear that each of these aren't a specific predicted line, that this is just sampled from information. So we wanted to ask participants, try to probe them in some way to see if they're using the conventions that they've learned here to understand this display. And I'll show you an illustration of how we would do that. This is the most simple hurricane forecast you've ever seen. There's 3 lines, and one of them is hitting your town. What is the probability that the storm will affect your town? Just call out any probability that comes to mind. 5%. Okay. Any other ones?
32.
Okay, right. Most people think 33. If you said anything other than 33, I would bet you a soda that you first thought 33, and then you knew this was a trick question, so you changed your judgment. But right, so most people say 33. Now in your mind, think to yourself, is there a greater chance that the hurricane will affect your home here than here? Okay, so this isn't some, tricky psychology experiment that I came up with. It was based on a real forecast that I saw. Here is a hurricane forecast from Irma. Remember I told you these were called spaghetti plots? These even kind of look like spaghetti noodles. They're the right color and kind of nature to them. Anyways, I was looking at this forecast and I thought, oh, well, shoot, what if you live here? What if you live on that island here? What do you do? Really, what would you do? Do you run over to your TV and measure how far away you are from the closest ensemble member? In our recent JAP Applied paper, we did a review of the 20 most watched hurricane forecasts for Irma, the ones on the news, and we found on average, people are shown these path visualizations for 1 minute and 54 seconds. So you have 1 minute and 54 seconds to make a life and death decision, and not one of those forecasts explained to the viewers how these were made or how to interpret them. So you're given no information, you're just shown this, you have 2 minutes to make one of the biggest decisions of your life. What do you do? What if your grandmother lives here? A little island, and one of those ensemble members hits her house. Say you have just enough money for one of you to evacuate. Does she go to your house? Do you go to hers? Do you send grandma inland? What do you do? And I mean, these are sort of hypothetical scenarios, but this is a real hurricane that affected people. This isn't a laboratory study. Okay, so we proposed a similar scenario to people in our lab. We showed a ensemble visualization with 2 locations, and we always had one of the locations directly hit by an ensemble member. And we asked, which location would receive the most damage, location A or B? Now, if people were to believe that areas closer to the center of this distribution should receive more damage, they would say B almost 100% of the time. And yes, we find people say B almost 100% of the time. But when we change the scenario, where the further location happens to be hit by one of the lines, further location from the central tendency of this distribution, what do people do? If they were to be using their same strategy, thinking that the closer location to the center would receive the most damage, they should say B 100% of the time. If they think that there is some true likelihood where this hurricane is going to follow this exact path and hit A, they'll say A some percentage of the time. People say A 36% of the time, people say B 64% of the time. Well, people are interpreting this as a list, a set of every single path that the hurricane will take, and it might take this path. They're not understanding it as a distribution or a sampling of information. So this gives us some indication that they're taking this type of schema and using it to interpret this visualization here. And this isn't unique to hurricane forecasts. We see this in other types of uncertainty research as well. Some of you might remember this New York Times election gauge. And when people first saw this from the New York Times, they thought that each one of those ticks back and forth was new information being fed into the model. They thought that it was maybe a new poll or maybe a candidate kissed a baby, something like that. The way that this was actually created was, I think, every 2 hours. It's either 2 hours or 24 hours. I forgot to look it up. But in any case, after some amount of time, they updated their model with all of the new information. The ticks back and forth aren't the model updating, they're sampled from a distribution. So they're trying to communicate the uncertainty with an animation. They're not giving you new information, which is actually very similar to what we're doing here. We're sampling from distributions of information to show you the range of uncertainty. We're not showing you every specific path that the hurricane would take. So very similar types of things going on here. And researchers have termed this a deterministic construal error, which is where you're presented with uncertain information, and instead of interpreting it as uncertain information, you're going to think about it deterministically. You're going to try to understand it as some type of concrete, defined information. Why? Because it's easier. It's easier than reasoning with uncertain information. There's an attribution error that's happening. You're swapping out something hard for something easy. So now what we want to do is try to improve the visualization in some way. This, again, is the wrong way to interpret this visualization, thinking that each one of those lines represents a real likelihood. So thinking a 33% chance here. So what do we do to improve this visualization? Now that we know that this is what people think, this is the miscommunication, the misunderstanding that they have, how do we use this information to change the visualization? Well, what we do is we simply add more lines. If they're going to come to the wrong conclusions, we'll still let them come to the wrong conclusions, but we'll tweak the visualization to capitalize on that bias and try to reduce the negative effects of that type of interpretation. That's one approach, and that's the work that we've most recently have in JEP applied. The other approach out there is to just train people how to understand these, and that's a reasonable approach as well. For me, I like to start first by making sure that information that we're giving to people is as easy to understand as possible and has the fewest amount of biases, and then going in and expecting people to get training and so forth. So this is always my favorite approach, is to try to improve the visualization before doing something like training. Do we see the same type of thing out there in the world? There's another tweet by President Trump. This was on September 4th. He tweets, "This was the originally projected path of the hurricane in its early stages. As you can see, almost all models predict it to go through Florida, also hitting Georgia and Alabama. I accept the fake news apologies." And this is the actual visualization created by this particular agency. Do you notice any differences from this one to this one?
Contrast.
Yes, exactly. This one has so much higher contrast, and it's much darker. Based on what I told you today, that people overreact when they see one of these lines hitting their point of interest, like Alabama. A way to magnify that effect is to up the contrast so you can see every single line hitting Alabama. So I don't know at what point this visualization was changed, who changed it, why it was changed, but this was what was produced by the visualization designers, and if you wanted people to overestimate the likelihood that Alabama would be hit, you would make the lines darker, okay? So, the other thing I want to point out is, to their credit, the people who made this also said, if anything on this graphic causes confusion, ignore the product entirely. So they are aware that this is a supplemental product to what is produced by the National Hurricane Center. And they've made it with that intention, really. The way that information is presented has a profound influence on our judgments. I showed a whole variety of examples where it is our jobs as information consumers to make sure that we are understanding the way that information is presented, being aware of all the different ways that visualizations can influence how we think and make decisions. Some of the items that I'd like you to pay attention to is always look at the legend, always check the labels to see if they're giving you some supplemental information about how to interpret it. Also, we're in a world where we need to try to go back to primary sources as much as possible. Visualizations go through so many channels in social media and everywhere else. At any stage, someone can manipulate that information. So if you're really using a visualization to make a decision, try to find the actual source and ensure to yourself that it hasn't been manipulated in any way. The other thing is, as scientists ourselves, it is our responsibility to make sure that the information we are producing is as easy to understand as possible and does not misrepresent our data in any way. With that, I want to give special thanks to all my many collaborators. In particular, these two are the folks who are responsible for all of those fancy visualizations that I've just talked about. A lot is on the job market, so smart recruiters might be interested. I'm accepting graduate students, so if you know anyone who is interested in this work, please let them know. Interested students can learn more about applying at space.ucmerced.edu. You can also find free access to all my publications there. And if you're interested in just updates on this work, follow me on Twitter. I'm very active, as you noticed from this talk. If you just want more information on these topics, a great paper of mine, shameless self-promotion, is a review paper from 2018 where I cover all of the decision-making literature on visualizations. It's entitled Decision Making with Visualizations, a Cognitive Framework Across Disciplines. And a nice pop side version of that is from one of my favorite people, Alberto Cairo. It's termed How to Lie with Charts. I just got a pre-press copy of it. You can pre-order it now. It should come out in a couple weeks. It's funny, it's entertaining, and you will learn how to be a more informed visualization consumer. Thank you.